Hello, everyone, and sorry for the delay. So today we're going to continue our discussions on demand paging, and there is not much left. So once we're done with this, we're going to start talking about I/O. Okay, so just an overview of what we talked about last time. We primarily focused on defining demand paging. We also talked about different algorithms for replacement policies, and we ended our discussions with how we can implement an approximate LRU. We talked about the clock algorithm, right? So just to review the clock algorithm, so we had all our pages around the clock, and then there is a clock hand which is pointing to one of them. Now we're looking at the valid bit of each page. Every time there is a page fault, we move the clock hand. We check to see if the page that the clock hand is pointing to has a valid bit of 0. If not, we change it to 0 and we move to the next one. Again, this doesn't have, we change it to 0. We move to the next one. Again, change it to 0 until we eventually find someone who is 0, and that would be our victim to be evicted. Now, let's talk about this clock algorithm that we've seen. Now, let's say I'm looking at the clock hand over a period of time, and I'm interested to see how fast it's moving. Now, if it's moving too fast, it means that if it's moving too fast, it means that I'm having a lot of page faults, because on each page fault, I'm going to move the clock hand at least once. Now, if it is moving slowly, this means that the system is good. I'm not having a lot of page faults. So this is a good indicator of how good the performance is. Because if you have a lot of page faults, that means that the performance is going to suffer, right? We discussed about all the costs that comes with demand paging. Now, one way of looking at the clock algorithm is that we're kind of putting all pages into two different groups. One group has a valid bit of 0, one group has a valid bit of 1 on every page fault. And the ones that have valid bit of 1 are safe. We're not going to evict them. The ones that have valid bit of 0, they're at risk. But then we're going to pick the first one of them in an order that the clock hand is advancing. Now, what if we want more than two groups, right? What prevents us from having only two groups? That brings us to the next, to an extension of the clock algorithm. We can run the clock algorithm by, instead of just looking at the valid bit, we can introduce a variable that counts the number of times that a particular page becomes victim. And every time a page becomes a victim, we decrease or decrement this variable. Now, if I initiate this variable to, let's say, 5, I'm not going to evict this file until this variable reaches 0. This way, I have given my page 5 chances to escape being evicted. Okay, it seems like my internet is not is having some trouble. Okay, I hope you're following. Now, here is how we're gonna change the algorithm. So as I said, we're going to again put everybody around the clock. Now, let's say that the clock hand is here, pointing to this page number, let's say 10. And let's say that the valid bit is 0. Actually, let's assume that, okay, I need the next one because the clock is moving every time I have a page fault. Okay, so now let's say this is the setting, and let's say this variable that I defined is right now 5. Now, give me a second. Maybe I have to close a bunch of applications, and that might help. Quick. Quick Firefox. Sky. Oh, this guy wasn't happy that I quit. And now it's happy. Okay. Okay, so I got actually a question. What does the access bit get set to? Oh, when does the access bit get set to 1? Is the access bit 1 when the page is first loaded? No. So it was in one of the slides that we had previously. So the address bit is set to 1 every time hardware does a page walk to find the translation. So we discussed about this in the previous lecture. So again, every time hardware searches for a virtual to physical address translation, and it doesn't find the translation in TLB, it does a page table walk. So it goes through the page table to find the translation. When hardware finds the translation, it sets the access bit to 1 and then caches the translation in the TLB. From now on, as long as the translation is cached in the TLB, the hardware doesn't go to page table. So the hardware is not going to set the access bit to 1 again. So that's the first one. The first time that the page was accessed, the access bit gets to set to 1. Now, the page could be accessed again and again and again and again, but then the translation is cached in TLB, so hardware doesn't go and do the page walk, so the access bit is not going to be changed. Now, that's why we said that in clock algorithm, if you want to set the access bit to 0, you have to go and also remove the translation that was cached in TLB. Because as long as the translation is cached in TLB, hardware is not going to come to page table to set the access bit again to 1. So we set the access bit to 0, and then we go to TLB. We remove the translation that got cached. Now, next time that the application or the process accesses that page, the translation is not cached in TLB, so hardware has to do a page walk, and then hardware comes back and sets the access bit again to 1. So that's how we know that the page was accessed from the last time we visited this page. Okay, so going back to this nth chance algorithm, so we define this variable, this track number. So let's define this as a track for this page. Initially, it's 5. Whenever so let's say initially it's 5. Now, I guess let's say yeah. Why am I doing this? Okay, so let's say this is now 0, and this guy is 5 for some reason. Now the head moves to this guy. Now so let's say a page fault happened. We advance the head. We look at this guy and we see it's 0. The access bit is 0. This means that this page wasn't accessed from the last time we came to this. Now, what do we do? In the original clock algorithm, we should evict this guy, right? We have found our victim, so we can evict it. Now, with nth chance algorithm, we're going to give this guy another chance. So we decrease this to 4, and then we move on to the next one, to the next page. Now, let's say next page is also 0, and the tracking value is also 0. So at this point, this means that this guy has used all of its chances, whatever number of chances we have given it. It has used all of them, and it still hasn't been used. So then we pick this one as our victim, and we evict this guy. So basically, introducing this extra tracking number allows us to give pages a chance to be accessed from the last time they were visited. And by doing so, we are creating more groups. Instead of just having 2 groups of those who have been accessed in the last time and those who haven't been accessed in the last time, now we have 5 or 6 groups. Those who have been accessed last time, those who haven't been accessed one time, but they were accessed previously, those who haven't been accessed 3 times in a row, those who haven't been accessed 4 times in a row, and those who haven't been accessed 5 times in a row. And then we can just pick the victim from those who haven't been accessed 5 times in a row. So that's the nth chance algorithm. Now, we have to be careful how to pick the number of chances that we're giving. If you pick a large number, so if you're going to give people a large chance, then there is a possibility that this clock hand is going to just rotate and rotate and rotate to eventually find a victim. This means that you're introducing delay in finding your victim, and page fault is already expensive. You're making it more expensive because you're just delaying when you're going to choose the file that you're going to pick. So sorry, and if this n is a small, the smallest would be just 1. So everybody has only 1 chance, and if it becomes 0, then we're going to evict it. Then your approximation is going to be less accurate to LRU. Okay. I guess there was one point I didn't talk about. Yeah, so I think I didn't talk about this. So in clock algorithm, going back to the clock algorithm, if everybody is 1, if all the pages have been accessed, for some reason, let's assume that all pages have been accessed. Now, what happens? Well, I'm going to start making them zeros. So I go to the first one, I make it 0. I make the next one 0. Everybody becomes 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. I come back to the first one, I evict it. Now, let's say next time I come again, everybody is 1. So I'm going to do again 0, 0, 0, 0, 0, 0, 0, 0, 0, and then evict next one. And then next time evict this one, and then evict this one, and evict this one. So basically, if every time I come, everybody has been accessed, then this clock algorithm is kind of like implementing FIFO. We wanted it to implement LRU, but as you can see, it's just an approximation. It's not actually implementing LRU. So in the case where everybody has only 1 chance, then our approximation is really off from LRU. The more chances you give pages, the closer your algorithm becomes, your implementation becomes to LRU. Okay, so I got two questions. I'm not sure if they're from the same person because both of them are like, I'm sorry. So sorry, I don't understand why we need to give more chances to pages for eviction. Why is creating these groups based off eviction attempts important? Right, so the reason this is important is if a page hasn't been accessed and you evict it, your assumption is that this page was not accessed from the last time I set it to 0. So therefore, it's not going to be accessed in the future. So that's your assumption. Now, this assumption might not be correct. Maybe it wasn't accessed in the past round, but it's going to be accessed right away after this. Now, if you give this page another chance, then it will be accessed next time and it won't be evicted. Now, if you get a page that hasn't been accessed for 5 times in a row, so 5 times you have visited this page and it hasn't been accessed, then it's kind of like you're like, okay, this page hasn't been accessed for a long time, so maybe it's time to evict it. So as you can see, the more you give chances, the more accurate your approximation becomes of LRU. Remember, LRU is the least the least recently used page. With just giving everybody one chance, you're not really finding the one who has been used the least. By giving people more chances, you will actually find the one that hasn't been accessed, for example, 6 times. Well, that tells you that this page hasn't been used for a while. But if you only have 1 and 0, then your approximation is not that accurate, right? So that's why it's important to give pages more chance, because that shows us, that gives us an opportunity to then compare pages that haven't been accessed for 2 rounds versus pages that haven't been accessed in 1 round versus pages that have been accessed in the previous round. So we have 3 categories. Now, if we give everybody 5 chances, then those who haven't been accessed for 6 rounds, those who haven't been accessed 5 rounds, those who haven't been accessed 4 rounds, 3, 2, 1, and 0. So now I can, have a better understanding of who is the one who hasn't been used for the longest in the past. Okay, so I got a follow-up question. So if there were some other way to write that access bit without doing a page table walk, would it? Oh, so this is, so I'm having trouble understanding why we would what is happening? Oh, okay, so this question was answered. So I don't understand why we need to give more chances. Okay, so this seems to be answered. Now let's go back to the other question. So I'm having some trouble understanding why we would invalidate the TLB entry. Okay, I know we want to see the access bit again, but doesn't it also mean that we are potentially doing a lot of extra page table walks? Yes, correct. So by going and invalidating the TLB, we are introducing more work for hardware. So we are making address translation harder, but we kind of need that. Don't forget, alternative is to wake up every page access to implement LRU. Now we're bringing it down to just let me know in a couple of times, right? I mean, even in this one, we're not asking hardware to wake the operating system up. We're just asking hardware to do the page walk again, which is less expensive than a page fault, which would wake operating system up. So again, the alternative is really expensive. To implement LRU exactly the way it should be is just too expensive. Okay, so if there were some other way to write the access bits without doing a page table walk, would it not be much better? Right, but unfortunately there is none, right? Okay, so that's that. Let's go forward. So we talked about nth chance. Now, one more thing to note is that we kind of have another bit that is also important, and that's the dirty bit. Now, let's say this page that I picked to evict, its dirty bit is 1. What does it mean? So if the dirty bit is 1, this means that I have to first write this page in the disk before I can evict it, because this page has been modified. Now, that is expensive, right? Because I have to wait for this to finish before I can evict it. So it's going to make my page fault handling even more expensive. So one option that we have is to use this bit as an extra chance, right? So once your chances become 0, then you're relying on your dirty bit. So if your dirty bit is set to 1, what I can do is I can just start a write back. So I can start writing this back to the memory, but don't wait for it, and advance my head and search for another victim. So instead of fixating on this guy, I can go and find some other victim who hasn't had a dirty bit, because that's, that's less expensive than waiting for this page to be written to the disk. Okay, now one question is, how frequently should we run the clock algorithm? So one option is the one that we just talked about so far, which is every time that you have a page fault, you run your clock algorithm. So that's the synchronous way. So every time I get a page fault, I run it. Now, the other alternative is to run it asynchronously, meaning that instead of waiting for a page fault to happen, you can start running, you can already identify who's the next victim, so that when a page fault happens, you already know your victim and you can just evict them. Now, this basically means that, periodically you can run your clock algorithm and then have a list of victims. So every time a page fault happens, you just pick someone from your pool. Now, if some page within your victim list is accessed, then you just remove them from your victim list, right? So that's pretty much what you're going to be doing. Okay. Now, we are kind of done with memory management. If you remember, I'm going to go back to when we started talking about memory after the reading week. If you remember, I said there are 2 main tasks with memory management. The first one was protection. So far, all our lectures have been on protection. And basically, protection boiled down to virtual address to physical address translation. That's what the majority of the course, the lectures have been focusing. Now, there was a second part in memory management, and that was allocation. So how do you allocate the available physical memory to processes? So I'm going to briefly talk about allocation, touching the surface. We're not going to get deep into it. It's actually a very interesting area of research, how to allocate memory, especially with data center applications. So before doing that, let me answer this question. So would asynchronous clock algorithm only work if you have a multiprocessor machine? maybe it would be less beneficial in a single processor machine because, yeah, I mean, yes, if you have only a single processor, it's better to just wait for a page fault to happen to run the algorithm. Because if you want to run the algorithm asynchronously, you might actually end up incurring more cost than just waiting for the page fault to happen because when you're running the clock algorithm, you're basically not running others unless you have a uniprocessor system and you only run clock algorithm when you don't have anything else to do, right? So that's another option. In that case, uniprocessor would also work. Let's say, the system is idle for a while, for a few microseconds. At that time, you can run your clock algorithm. So that's also a possibility. But probably in those situations, you don't want it to be periodic. You just want to make sure that you only run the algorithm when there is nothing else to do in the system. That was a good question. OK, so let's start talking about allocation. So how do we allocate physical memory between different processes? So what fraction of physical memory should we allocate to different processes? Now, each process needs a minimum amount of physical memory to be able to run, right? So if you cannot, for example, fit in the code of the process, it's not going to run. So there is a minimum amount of physical memory that you need to give a process to run properly. Now, you could leave allocation to how much processes use memory, right? By that, I mean you could just not enforce any allocation to anyone. Don't say that process 1 gets, I don't know, 1 gigabyte, process 2 gets 500 megabytes, process 3. Don't say that. Let them compete. Now, how does the competition work? Well, if you have a process that needs a lot of pages, this process is going to use a lot of memory. And then if the memory gets full and this process wants another page, then you're going to trust your replacement policy to find a victim, to evict and bring the new page. Now, who is going to be the victim? Now, this victim could be a page from another process. In that case, you're giving some of the memory you had given this other process to the first process. So let's say you have process 1 and process 2, and process 1 wants to bring a page, and the victim is from process 2. Now, if you evict a page from process 2 to bring a page from process 1, this basically means that you're allocating to process 1 more memory, and you're taking that away from process 2. And this is done by your replacement policy. So if you leave it to applications, then you might end up in a situation where if you have one aggressive process that needs a lot of pages, it could take away memory space from other processes and then make them suffer. An alternative to this is to make sure that the replacement policy only picks a victim for the same process. So if the memory is full and I need to find a victim, I'm going to find a victim among your own pages. I'm not going to go and find a victim from somebody else's pages. So this is one thing that has to be considered. So it's not just how much memory you initially give processes. You have to also enforce replacement policy to pick the victims among the pages for the same application, for the same process. Otherwise, you could start with everybody gets equal allocation, but then one of the processes is aggressive, it goes and takes away memory space from other processes and it slows them down. So it's not just important to give them a minimum when they start, whatever you're giving them, you also have to enforce that in your replacement policy. So the two options that I have in the slide is the global replacement, where you can find your victim among any page. It doesn't need to be among your own pages. It could be among somebody else's pages. Versus the local replacement, where we focus on finding a victim within the same process. So if this process wants to bring a new page, it has to evict one of its already using pages. Now, one way of allocating memory is fixed priority allocation. So basically, you fix the allocation of your processes. Now, there are options for this. So you could, so here in this slide, I have three options. The first option is equal allocation. So you basically divide your physical pages among your applications. So that's one way. Everybody gets equal. We discussed how this is not a good policy, because somebody might not need their allocation and somebody might need more than their allocation. So then the other alternative is proportional allocation. Now this one says, I'm going to give you memory in proportion to your priority. Now, what is your priority? Well, you can define different kinds of priorities, right? This priority could be something that your programmer says. So maybe your programmer says, I have these two processes. This process, the weight of this process is twice as much as this process. So it could just be that you design an API and you ask your programmers to set these weights. So that's one way. And then you allocate based on the priorities. I guess I'm actually talking about this one. So this is the priority one. So so that's one. Or you could do based on how much they consume, how much memory they need, and then you allocate in proportion to their needs. So that's another thing, right? So this is basically this allocation according to the size, where I can just see how many pages my process needs, right? And this is the total available memory. I give everybody their fair share based on how much they need, right? So if you need SI and I have M pages, then SI times M divided by capital S, where capital S is basically sum of all SIs. So these are fixed priorities. Basically, you allocate and then you make sure that everybody gets their allocation and the allocations don't change. Now, the problem with this is that applications and processes go through phases, right? So your application might be in a phase where it needs a lot of memory, and then it goes and does some computation. So in another phase, it might not need much memory. And then it's done with that phase, it goes to another phase of memory. Now, if you fix the allocation of your process, then in the phase that if your application changes phase, there's a chance that it really doesn't need the memory that you gave it. And then it goes back to needing it, and then it goes back to not needing it, and so on and so forth. So you could potentially, instead of doing a fixed allocation, you could do adaptive allocation. So you could potentially track how much memory your application needs, and then do the allocation according to that. And if the demand of your process changes, its allocation also changes. Now, This is something that we saw in the previous lecture when I was talking about the anomaly that we saw in FIFO. It's usually the case that the more you give, so in this picture on the x-axis I have the number of pages that are allocated to a process. On the y-axis I have the number of page faults. And then we discussed this, that the more you give, you expect the page fault to come down, right? Because there is less competition for the pages. There is less conflict. Now, we could use this to establish what is acceptable for different processes. So not all processes have the same curve. So for one process, this curve could be like this. For another process, the curve could be like this. For another process, the curve could be like this. Now, we can set this range of acceptable page fault rates. So we can say this is a range that is acceptable for processes to have this range. Now, if I define this range, I can look at my curve and look at this these ranges. So these become the ranges of the allocation I want for each process. So this means that, let's say this is for process 1, this is for process 2, and this is for process 3. This means that I need to allocate something between this and this for process 1. I need to allocate this much memory. So don't forget, this is number of pages. Number of pages. So probably for process 1, I need to allocate, I don't know, I'm just making it up. The numbers are made up. Something like 10 to 20. Obviously, it's much more than that. And then maybe for process 2, I need to allocate, I don't know, 5 to 8. And then for process 3, I need to allocate something between 2 and 3 number of pages. Now, once I have this range, I can see if I can allocate everybody the maximum. Maybe I have that many pages, so I will give everybody their maximum. If I don't, then I pick something in between that satisfies everybody, right? So I try to fix this. Now, so this is just, this is just theoretical, obviously, because we're looking at this graph and we're assuming that I have these, these curves. In reality, when you start running your application, you don't have these curves, right? You don't know what the curve is. So what can you do in practice if you don't have these curves? What you could do is you could, let's say you don't have the curve. So you start with something, you start giving your application some number of pages, and then you measure their page fault. So you see how much page faults they're experiencing. If it is really good, let's say if it is, so let's say your range was between X and Y. So if your application is getting less than X, this means that you probably have given this application too much memory. So start reducing the memory until you bring the page fault rate within the range that you have, X and Y. If what you did initially gave your application a lot of page faults, this means that you haven't given your application enough. So start giving your application more and try to bring down the page fault rate. So that's what you could do in practice if you want to implement such a thing, right? So you start with some estimation of how many pages your application needs. Then you measure their page fault rate, and then you play with the allocation to get the page fault rate within accepted range. So that's another thing that you can do if you don't have the curves. So what is thrashing? So, I have a question here. Is priority allocation a type of fixed scheme allocation? Right. So yes. So any allocation that you fix somebody's allocation based on whatever you want. So let me go back. So we have two classes of allocations: static and dynamic. So I think the words that I have used here are, fixed or adaptive. This means that whatever you're allocating your application, you're not going to change it during the life cycle of your application. So you allocate some fixed memory to your application and you don't touch it. With dynamic, it means that as your application goes through different phases, you're gonna change its allocation. So these are the two terms that I used. Now, in this slide, we talked about fixed priority allocation, right? So fixed priority allocation could be implemented statically, it could be implemented dynamically. So with a static allocation, you just look at everybody's priority and you allocate and you don't change it. With adaptive, you allow priorities to change, and as the priorities change, you change the allocations, right? So fixed priority is an allocation mechanism. You can implement it statically, or you can implement it dynamically or adaptively. I hope I didn't confuse you even further. Okay. So what is thrashing? Thrashing is a situation that happens, and you probably have seen it. I mean, for those of us who had really old systems, this happened a lot. So you start opening new processes, like you start opening your Firefox, your Word, and then you open your Photoshop, and then you open your, I don't know, Adobe, and a lot of application. And at some point, your system crashes. Your system becomes not responsive. So what is happening? So why is opening a lot of applications, even if I'm not using them, what is happening that is bringing my my system down? So what is happening is basically thrashing that is happening. So each one of these applications that you open, it needs some number of physical pages to run. And as you open more and more application, or even you can actually think about multi-threading or multi-programming. As you increase the number of programs in your system, your CPU utilization goes up, obviously, because you have more work to do, right? So you're going to make use of your CPUs. Let's say you have a multiprocessor. You open up more applications, well, they're going to run on CPU, so CPU is going to get more utilized. And then at some point, your system crashes, right? Like it doesn't do anything useful. It's still working, but it's not doing anything useful. What is happening at this point? At this point, what is happening is that you're doing a lot of page faults. So, one application kicks another application page out, and then that application comes and kicks somebody else's page out, and that somebody else comes and kicks somebody else's, and then you have a loop. So most of the time goes to do demand paging. Most of the time on the system goes on swapping pages to disk and bringing new pages, and then again and again. So that's what we call thrashing. You're thrashing your memory. So how can you detect this? Well, obviously, you know when it happens, right? You definitely will know when it happens because your system is not gonna work. But if you want to really avoid thrashing, you should take measures by not allowing this multi-programming to advance. You have to cut it at some point. Now, what does it even mean? How can I cut multi-programming at some point? It means that I'm going to have to not allow the number of processes in my system to grow out of bound, right? Because if it does, then I'm going to start thrashing. So this is one thing that I kind of mentioned multiple times during the course. This is kind of like swapping the entire process to the disk, to the permanent storage. So not so far with demand paging, we have been talking about swapping one physical page to hard disk and bringing another one. Now, at some point, you might want to swap an entire process, basically blocking them from further execution. It's not blocking, it's called swap. So you swap the entire process out. You say, okay, I'm not going to run you because I don't have enough memory. And by doing that, you're hoping to come and recover from this thrashing. So then you bring yourself here, you then finish some processes, and once those processes are finished, then you bring the process that you swap to hard disk back. So again, when thrashing happens, we definitely want to do something. So we want to respond. The best response is basically to sometimes you can take measures of killing processes. That might be too harsh to start killing processes. It actually is an option in Linux, but you really don't want to do that. So another alternative is to swap the process. So basically make the process go and wait for a little bit until the demand on memory is low and you can start running. Okay, so I got another question here. Can we implement proportional allocation dynamically too? Yes, obviously. I'm actually going to talk about that. So can the size of process change during runtime? Yes. So the size is not going to change, but the work set is going to change. So it's coming. Yes, that was a good question. I'm going to talk about it. About some notion of dynamic implementation of proportional allocation. I'll talk about it. Okay. Now let's talk about the question that was asked, actually. Let's talk about working sets. What is a working set? So in this figure in front of you, I have on x-axis, I have execution time. So this is execution time. On y-axis, I have memory addresses. So from 0 to whatever. So any point here, any single point in this graph shows me that this address was accessed at this time. So at this time, at t, I accessed this address. So this is what this graph means. So I looked at every single access at any single time, and I put a dot for that. Now, what does this show us? We can look at this graph and talk about working set. So look at these boxes that I have put around the points in this graph. What does this mean? look at this box. Every single box kind of is indicating that in this period, so here I have a delta t, there is a range of address, delta A, that I am accessing a lot, right? So look at these points here. So these points mean that in this time period, I kept using this range of addresses. This is basically temporal locality and a spatial locality in action, right? We are seeing it. Now, the behavior of the application changes in this other time. So I start needing more addresses or accessing more addresses in this other time period. So this is delta T1, this is delta T2, this is delta A1, and this is delta A2. So that's the meaning of these boxes. Okay, how can I use this information? Well, if I allow these addresses to come to memory, if I allocate enough memory to bring this data to my memory, what will happen to my application's performance? Well, the performance of my application is going to be boosted. The performance of my application is going to go up because the addresses that it needs are in memory. It doesn't need to go and grab them from disk. So this basically tells me how much memory I kind of need for my application to perform smoothly without needing to do demand paging. Now, at any given time, I can bring this window, I can move this window and look at all these addresses that I probably need. So I don't have all of them. So there are some here, some here. And this shows me what are the addresses that are frequently accessed at this duration. And if I bring these to memory, I'm going to speed up my application. This is called, so these boxes are called these are indicators of the working set. So a working set is a set of pages, or basically these addresses, that are accessed in a sampling time window. So that's the definition of working set. Now, if I look at my hit rate in memory, how often do I find the page that I need in memory? And then I look at my memory allocation. Obviously, if I give more memory to my application, the hit rate is going to go up, right? The max is I give the entire memory to my application, so its performance should be the best, right? Now, you can see these jumps. What are these jumps? So these jumps are basically the times where I can fit a working set in my memory. So let's say the first one here, I give enough memory to bring this working set to memory. So my performance all of a sudden jumps. When I bring this working set to memory, all of a sudden my performance jumps. Now, I need to then give another chunk of memory to bring my other working set. So while I'm increasing my memory, at some point it can fit my next working set, and then my performance again jumps. Don't be confused. I'm using hit rate and performance interchangeably, obviously, because if my hit rate is high, then my performance is high too. And if my hit rate is low, my performance is low too. And again, for this working set, I now need a lot of space. So as I'm increasing, I still haven't fit the working set, but at some point I will hit the working set and then I get another jump. And so on and so forth. Then I go for this one, so I get another jump. I increase my memory and I can fit this one, I get a jump. and so on and so forth. So that's the explanation for these two graphs in this slide. Now, how can I know what is my working set, right? How can I know how much memory my application needs? So one thing to do is to keep track of all the pages that your application needs, and then say that is your working set, right? So basically, at any given time, T1, I look back for some delta time period, and I look at all the pages that were referenced. And I construct a set of all pages that were referenced. So in this example, page 7 was referenced a lot, so I pick one of them. So I have 1, 2, 5, 6, and 7. Now this will tell me approximately what my working set size is, right? So at this point in T1, my working set is around 5. I need 5 pages. Now at time T2 here, I look back at this delta time, and I look at all the pages that I needed. In this case, I needed 3 and 4, but as you can see, I used 3 a lot, I used 4 a lot. So my working set has shrinked. Now I don't need 5 different pages, I only need 2 pages. So now going back to the question that was asked, can we do proportional allocation dynamically? Here it comes, right? So instead of using the size of process, instead of using all the pages that my process needs, I can just look at all the pages my process has been accessing for the past few microseconds or few milliseconds or whatever this time window is, and then do my allocation based on these. So based on these working sets, I then allocate to my processes. So right. Now, how big should be this this period that we're going to go back and look at? If this period is too small, then we're not going to get good information, right? Because we're kind of forgetting about past. If this period is too big, then we're remembering too much. Maybe, if I go this much back, then there were some pages that I used and I'm no longer using them. And considering those in my working set is just waste. I'm really moved on from that phase of my application and I don't really need them anymore. So you have to find like some sweet spot on what this delta is, depending on your system, depending on the type of applications you're running, and so on and so forth. And if you set this delta to be infinity, then we're back to just what is the size of my process, how many pages my process uses, which is kind of it goes to the fixed allocation paradigm where you statically allocate, for example. Okay. Now, this also will help us track if our system is getting into thrashing. So if I sum up all the sizes of these working sets, so if I know that the size of working set for process 1 is 10 pages, the size of working set for process 2 is I don't know, 20, and so on and so forth. And then at the end, I sum them up and I'm like, okay, I'm using 1,000 pages. Then if the size of memory is less than this means that I have started thrashing because my processes are needing more pages than I have available. So probably it's a good indication that we might want to swap a process out to disk to bring the demand down. And if it is not, then this means that, okay, things are going well. I have enough memory and the system is not getting into the thrashing. Okay. Now, I guess I have kind of covered this in the past, so I guess I'm going to move on. I'm a little bit running out. Okay, so the last topic I want to talk about before ending this lecture is about the core mapping problem. So with page tables, we go from virtual memory to physical memory. Sometimes we actually need the reverse. We need to go from physical memory, physical address to virtual address. Why would we need such a thing? Well, when you're doing demand paging, when you're removing a physical page from your memory, you probably want to go and invalidate page table entries. Now, if you remember, we had these situations where we had memory sharing, for example. So bunch of processes were sharing the same page. Now, if you swap this page to permanent storage, you have to go and invalidate this page table entry in all of these processes page tables. So it's too much to every time you every time you remove a page or you swap a page, you don't want to go through all processes, go through all of their page tables and see where this page was mapped. So to avoid this, you want to have the reverse as well. So you don't just want to know from virtual to physical, you also want to know the mapping from physical to virtual. So this map is called reverse page mapping. So it kind of is the reverse of page table. Page table translates virtual to physical. This reverse page mapping gives you from physical to virtual. And the primary use is whenever for example, when you do demand paging, you can then find exactly which page tables you have to change instead of having to search all your page tables every time. So right. Okay. Right. So there are different different implementation for this, but then the idea is what I just described. Okay, so I think we can. How much time do I have? I really wanted to. I think we spent so much time on. Okay, so next topic is I/O. At least let me start I/O before the end of today's lecture. Okay. So before we get it started, I have a lot of slides for I/O. How many slides do I have? I actually have. Oh, what happened? I have 63 slides for I/O, but I will probably not be able to go through all of them. So I will let you know which slides I don't cover. So there are so much material here for I/O. And unfortunately, I won't be able to cover all of them because of time, because I also want to talk about file systems. So we'll see. So let's get started. We're going to talk about, so okay, this is a new phase of the new topic that we're going to cover. So we're done with memory management. Let's talk a little bit about I/O. I wish we had more time. Unfortunately, we don't. We spend so much time talking about concurrency. Please, if you are pulled on this, tell the director and the program director that you guys should have known about concurrency before, and then because this is an operating system course, but that's another topic. Okay, so we're going to talk about I/O subsystem. This part is a part that I'm not going to cover, so I'm not going to cover about anything about I/O performance, unfortunately. And then we'll talk about storage devices. Okay, so let's get into it. These are just introductions, so I'm going to jump. A little bit of trend technology background stuff. So it's a computing system is useless if all it has is a CPU and a memory, right? A computer system becomes a computer system when it has input and output, when users can communicate with the device through giving it input and then expecting from it some output. Now, how many different devices are there out to be used as an input and to be used as output? Your camera, your mouse, your keyboard, your microphone, your USB card, all of these are sources of input. These are devices that provide input to your computer, and then all the sources of output, like your your display, your sound system, your printer. So these are all the interesting things that are possible because our systems can provide input and output. Without these, if you only had a CPU and a memory, then your system wouldn't be interesting and useful at all. Now, there are so many different types of I/O devices. There are so many types. And then with these different types comes different characteristics. Not all our I/O devices are the same. Like in this particular slide, I'm looking at the transfer rate of different devices. So basically on the y-axis, I have gigabyte per second. So how much data can you transfer between your device and the memory system, or the CPU? And then on the x-axis, I have different types of devices. So you can see that at the bottom of this spectrum, you have your keyboard, you have your USB, your Bluetooth. These are devices with really low transfer rate. There is not much data being transferred. And then on the higher end of this spectrum, you have the PCIe devices that you have. These provide really exceptionally high data transfer. In fact, we're going to talk a little bit about PCIe devices. Now, as you can see, there's an order of magnitude difference between these, and this is just one aspect of I/O devices. This aspect of their transfer rate. Now, there are so many different aspects to talk about. Really, the protocol that you talk to your device. Different devices have different protocols. So the point being, as an operating system designer, we are faced with this challenging job of providing unified interface for all different kinds of I/O devices. Now my little girl has come, so I don't exactly know what's going on. Now she went upstairs, so I think she woke up and she wanted her dad, and she's crying. I think her mom came, so I'm definitely gonna go to her after this, so in 8 minutes. hopefully her mom takes care of her. Okay, so yes, so as an operating system designer, we definitely want to hide all these different complexities from our application developers. And also we want to let hardware designers and architects and device designers to provide as many different types of hardware as they want. So we don't want to kind of restrict everyone to provide certain range of data transfer or certain range of protocols. We want to let them have as many and as diverse as possible. But then this basically makes our life harder as operating system designers. So we are faced with these different kinds of devices. What is the goal of I/O subsystem in an operating system? Now, the end goal, as I described, is to provide this unified interface. Now, this unified interface has to be able to communicate with different range of devices. Now, this unified interface in Linux and in Unix kind systems is basically file interface. We're going to assume that all our devices are just files, and we're going to read and write to and from these files. So this way, we don't really care what device it is, how fast it is, what protocol it implements. We're going to just treat them as files. We're going to map them to certain file address. And then we're going to open them, write to those files, read from them, and then close them. So this is the goal. This is the goal, and this is how actually operating Linux, at least, or Unix-like operating systems treat different devices. They map them to file addresses, and they communicate with them through through reading and writing to those files. Now, for ECE students, they actually, they do all sorts of cool projects with this, but in 252, not in 350. But I guess if you guys are interested, you have to just do the reading by yourself. I'm just, scratching the surface here because of the lack of time that we have left. Okay. Now, let's talk about different aspects of I/O devices and how they're impacting us as operating system. The first one is the granularity of data. How are we talking to our devices? Some devices, you can talk to them byte by byte, so you can read write 1 byte at a time. Some other devices, you can read and write blocks. Now, what is a block? It will depend on that device. But for example, if you're working with your SSD or your disk, you don't read and write 1 byte. You usually read and write a sector, for example, or a block of data. The same with your networking. So you create a packet and you talk to your NIC in a granularity that is much more than a single byte. The other thing is the access pattern of your device. Is your device allowing you to have sequential access to the data, or can you? Is your device restricting you to have sequential access to the data, or does your device allow you to access random data? For example, just an example, if you want to, have a, let's say you have a DVD and you want to read. Now, usually you can move the head of, so where you're reading in your DVD, that could jump. So you have random access to all the data available to that DVD. But then back in times, I myself never used these tapes. So these were, old generations of storage. So with these guys, if you wanted to read something in the middle of the tape, you couldn't jump to that. You had to start reading from the beginning until you get to the middle. So you didn't have access to do this jump. So that's another thing that we have to be aware of. What kind of access pattern does this device provide? The third one is, how is this device going to talk to us? Some devices are polling based, meaning that the device is not able to raise an interrupt. The device cannot interrupt the processor. In those devices, you have to always poll the device. So you have to always, the CPU cycle has to be gone to checking a certain address, which might be mapped to a register in the device, to see if the device is ready, or if the device has done what you told the device to do. Most of the devices that we have are in today's systems are capable of producing interrupts. So they can raise an interrupt and tell operating system that whatever you wanted is now ready. So these are more probably, if you care about performance and utilization, these are really things that you have to consider. Now I have a few more minutes. I'm going to still go because I'm really behind. So let me go a little bit further in time, if you don't mind. I prefer to cover these slides than just leaving them. So I'm going to go 5 minutes above the threshold of the class. So if you need to go, please feel free to leave. The videos will be available, so you can come and watch this 5 minutes. Okay, so let's focus on the data access. Some devices, as we discussed, are byte addressable. So the unit of transfer is a single byte, a single character. So for example, these are some of the examples: keyboard, mice, your serial port, some of the USB devices that you have. These are byte addressable. So they communicate byte by byte. Now for these, usually the commands that we use are get and put. So if you want to write, you use put. If you want to read, you use get. And this works with a single byte. If you have block devices, if you have devices that work with bytes, with blocks, then you don't need to, iterate through your data byte by byte. You can create these blocks and then transfer the entire block to your device. Usually for these devices, the commands that we have are the file commands that we saw: read, write, seek, open. These are the ones that we're going to use. There is a third category of devices that are distinct from both of them. They're distinct from byte addressable and also block addressable. These have their own category, right? This is basically your network devices, and they kind of support both. And usually the interface is not get, put, or read, write. So they have their own interface, which is socket interface. Again, unfortunately, we don't get to talk about sockets. This is a topic that is covered in EC 252, which I am pushing for SE to also have a version of it. That's why I'm just advocating you guys to also raise this issue. But yeah, so unfortunately we don't get to talk about it, but it's a very important topic, and some of you might have already done some socket programming, but this is a different kind of devices that the operating system has to provide services to. And that's the whole category of socket system calls. You create a socket, you connect to a socket, you disconnect from a socket, you listen on a socket, and these are all system calls that the operating system provides, which we're going to not talk about, unfortunately. OK, now let's go to timing when it comes to the I/O devices. So I guess we talked about this. You probably have it actually in your lab. So some calls are blocking, right? So when you read or when you write, you get blocked, right? So if you want to, for example, read from a SSD, you could have a blocking read, meaning that you're going to tell the operating system that I want to read this byte, and until it's ready, I don't have anything else to do. So put me to sleep. So when you call read, then you're going to be blocked, because I'm going to now go to the device and bring your data. Or when you do a write, you're going to get blocked until your data is written, and then once it's done, then you can continue. So this is a blocking interface that operating system provides. On top of this, operating system could provide non-blocking interfaces. What does this mean? This means that you're going to tell the operating system that I want to write to the file, but I also have other things to do. So initiate the write and let me run. So these are non-blocking calls. And again, operating system has to provide this. This is another topic that is covered in ECE 252. I guess when I say covered, is that students actually work with these system calls. So they actually use these asynchronous system calls to do non-blocking I/O. But at this point, I'm going to just tell you, and you're going to just believe me that these exist. There is also oh, I'm so sorry. So the one that I was talking about is asynchronous interface. With non-blocking interfaces, it's kind of like you say, yeah, so with the non-blocking ones is that if it is not ready, don't wait for it, right? So if it is ready, for example, if you want to read, if your data is not in memory, you just say, okay, I don't want it anymore. So just return unsuccess, and then I continue. If you want to write, the same. You just say, write this, and I'm not going to wait, and then you continue your execution, and you don't care. Either the write goes and is successful, or it's not successful. You don't wait. And then there is the asynchronous ones, where you say, initiate this process for me, and then later on come and let me know once it's done. So you initiate a read, you go do some other things. Once the read is done, the operating system has to come and tell you that the read is done. What you asked me is done. Now do whatever you wanted to do. So these are the asynchronous interfaces. These are very actually handy these days in cloud computing and data centers. OK, so I'm over that 5 minutes that I said. I'm actually 7 minutes into this. Sorry for that. So thank you for sticking around. We'll talk to you on next Tuesday. Take care. Be safe. Bye.